Well, it was quite a Super Bowl last night, huh? Here in Minneapolis, the Eagles beating the Patriots. I think it was. I saw that it was the most yards ever in even a playoff game. I'll have to look up and see if it's the most, close to the most yards ever for any game. Pretty amazing. I think I'd like to start today by looking at one of the problems on the homework assignment that I was turning back to you, and looking at the one that I gave you the hint on. Dealing with defining the inverse function and showing that it satisfies the kinds of properties that you want. So you were given a function alpha whose domain is A and whose codomain is B. And you're also given in that last part of that problem that alpha is 1-to-1 and non-to. By the way, you can abbreviate 1-to-1 as 1-1. Just be careful to make the dash clearly in between so it doesn't look like an H. Otherwise I may. I'll probably figure it out, but okay. If there were some other grader, they might think it's an H. That's 1-1 is 1-to-1 and onto. The goal is to show that there exists a function labeled alpha inverse going from B to A such that it has the properties that alpha inverse of B always equals B. I'll take it. For all little b and capital B. And alpha inverse alpha of A equals A for all little a and capital A. Okay? And you do need to define, you need to describe, it's a big part of the point of the problem to describe how to define alpha inverse. It's not meant to be difficult, but it's just a little tricky to realize what you need to do at first. It's really the fact, first of all, so here's the proof. You can say that since alpha is onto, well, okay, I should start by saying let little b be given. Okay, you can draw this picture here. Here's A, here's B. Alpha maps from A to B. You're given a little b over here in capital B. You want to say what alpha inverse of little b should be. Since alpha is onto, you know there exists a little a and capital A, so that the image of A under alpha equals B. Given any b in capital B, there's something over here that gets mapped to it. But there could be more than one thing that gets mapped to it. Well, no. Since alpha is 1-to-1, there can only be one thing. Since alpha is 1-to-1, this little a and capital A is unique. I split this into two sentences. You could have written this in one sentence. You could have said, since alpha is 1-to-1 and onto, there exists a unique, you could use this notation, there exists unique, exclamation point, it's not a factorial. There exists a unique A in capital A so that this is true. I split this into two sentences, but you could have done one sentence. Define alpha inverse of B to equal this unique little a. That's defining the function alpha inverse. Then you need to verify that these equations are satisfied. And they are pretty obvious if you think about it, but I'd say at least one of them deserves a little explanation. Which one? Well, let's look at this one first. You could say for any little b and capital B with corresponding little a and capital A, I'm being a little extra wordy here, alpha inverse of B equals alpha inverse of B, which by the definition in the previous sentence equals alpha of A. But alpha of A, by definition, is B. A and B correspond to each other. It's this way that requires a little extra explanation, I think, to be fully rigorous here. Why does this equal A? I could write alpha inverse of B here and say that must be A, but I think it's better to emphasize that this equals A right away by saying since A in capital A is the unique element of capital A, mapping to what? Again, you can call it B, but you can also just call it alpha of A. A is the unique element of capital A that maps to alpha of A, which we've called B. Therefore, by definition of alpha inverse of that thing has got to be the A. It is confusing, okay? It is a bit tricky, but that really is the reason. And to be fully rigorous, I think something like that should be said. Again, the picture can help. Alpha of A maps to some element alpha of A, and that is the unique element of capital A that gets mapped to alpha of A. Therefore, alpha inverse of this thing must be A. I think maybe this was maybe a little too much to expect. I think I gave people full credit even if they didn't add this little explanation here. And maybe nobody did, I don't remember for sure. But ideally, that's what the kind of thing that you're shooting for. Okay? It's not easy, okay? It's confusing. You got to think really, really carefully about concepts. But I did take off points if you didn't really describe how to define alpha inverse based on the fact that alpha is assumed to be one-to-one and onto. That is essential. All right. Any questions at all? Let's review groups and examples. Actually, today it's going to be mostly a review of what we did on Friday in more depth. Okay, but I think that's really necessary. We need to redo a lot of these things, maybe with some new examples, to really start to get this stuff more in depth. Okay, so this is knowledge that you should have both now and in the future. The integers, the rationals, the reals, and the complex numbers all form groups under addition. We should probably think about non-examples too. You know what a non-example is? A non-example is an example where something's not true. You could ask, does Z, the set of integers, it's still the same set, form a group under multiplication? That dot's supposed to represent multiplication. Maybe you prefer an X here. We should think about those kinds of examples too, and sometimes they're called non-examples. What do you think? Do you think Z forms a group under multiplication? What's it got to have? It's got to be a binary operation. Combine two integers, do you get an integer under multiplication? Yeah, it's a binary operation on Z. Is it associative? It's A times B in parentheses times C equal That where you do the b times c first? Yeah, that's true. Does it have a multiplicative identity? Wouldn't be 0. What would it be?
1.
It would be 1. Yeah, it's got a multiplicative identity. And 1 is an integer. How about multiplicative inverses? There we're in trouble. Everything except plus or minus 1 has no multiplicative inverse that's an integer. There is no integer a, so that 5a equals 1. Of course, there's a rational 1/5, such that 5 times 1/5 does equal 1. But there's no integer. This is not true for all integers a. So the only thing that doesn't hold is the existence of multiplicative inverses. Except for plus or minus 1. Plus or minus 1 have multiplicative inverses, but no other integer does. So it's not a group. Well, okay. 5 didn't have a multiplicative inverse that's an integer, but it does have a multiplicative inverse that's a rational number. Does the set of rationals form a group under multiplication? Got closure still? The product of two rationals is rational. Associative property still works. 1 is still a rational number. It equals 1 over 1. It also equals 7 over 7. That would have a multiplicative inverse now, right? 5 times 1/5 does equal 1. 2/3 has got a multiplicative inverse. It's 3/2. This product equals 1, multiplicative identity. It's looking good, isn't it? Or is it? I keep looking over there since the bulk of you over here. I want to look over here sometimes too. Or is it? Do we have a problem or not? You think this is a group?
No, what about 0?
Yeah, 0 doesn't have a multiplicative inverse. 0 times a does not equal 1 for any rational a. Just that one number messes it up. So take it out. Q star is by definition as a set defined to be Q take away 0. This set does satisfy the properties of a group under multiplication. Not under addition though anymore, because you took 0 out, you took the additive identity out. So it's not a group under addition, but it is a group under multiplication. Groups are more than just sets, they are binary operations on the set that satisfy certain properties. Addition no longer satisfies the group axioms here, but multiplication does. It's good to keep non-examples in mind as well. Or sometimes they're called counterexamples, though that's a word more typically reserved for showing a certain if-then statement is false. Zn under addition mod n. The general linear group, GL2R, of non-singular 2 by 2 matrices with real entries under matrix multiplication. Remember, non-singular means invertible. Remember from linear algebra? It's a little strange. Non-singular means invertible. Singular means non-invertible. The origin of the word singular in math is kind of related to something's a singular phenomenon if it's kind of rare. Singular matrices are kind of rare. I mean, in the sense that if you put numbers in a matrix, a square matrix randomly, most likely it will be invertible. Its determinant will be non-zero. It'll be invertible and therefore non-singular. It would be rare, maybe even unheard of, impossible if you're truly doing things at random to put numbers in a matrix and have it be non-invertible. Have it be singular. if you were truly doing things at random. Of course, we can do things non-randomly too, and make singular matrices. Under matrix multiplication, that's group 2. Certain collections of functions under function composition. We looked at an example like that last time. There will be plenty more. Here's a new group. We've never seen this before. Light off for the moment. Let U of n be the set of all positive integers less than n that are relatively prime to n under multiplication, under the operation of multiplication mod n. Un is the set of all positive integers less than n that are relatively prime to n as a set. The operation is multiplication mod n. I claim this is a group. I'm not going to prove it, but I claim it's a group. We'll look at an example. It's called the group of units modulo n. Little warning though, the symbol U of n can also be used for another kind of group. It can also stand for what's called the unitary group of all unitary matrices under matrix multiplication. You've probably never heard of a unitary matrix unless you've taken quantum mechanics. They generalize the idea of orthogonal matrices to a situation with complex number entries. Let's look at an example of this. N is any positive integer. I think n has to be bigger than 1 for sure here. Yeah. Take U8. By the description that you see here, this is supposed to be as a set, the set of all positive integers less than 8 that are relatively prime to 8. We briefly talked about relatively prime at the end of class last Friday. Two numbers are relatively prime if, can you say it really quickly? Yeah, the GCD, greatest common divisor, is 1. They have no prime factors in common. Another way to think of it. Well, 1 is neither prime nor composite and has no prime factors, but we include 1 in as being relatively prime to other numbers. So it's got 1. I just don't want numbers that have 2 as a factor, right? 8 is 2 cubed. So I'm looking for numbers less than 8 that do not have 2 as a factor. They're not even. 1, 3, 5, and 7. I claim this is a group under multiplication. I'm not going to prove that, but let's do a few calculations in this to at least help us believe the closure aspect of it. I'm doing things mod n, mod 8, multiplication, not addition. We've only been doing addition so far, mod n. Now we're doing multiplication. 3 times 3 is, of course, 9, but what is 9 mod 8? What's the remainder when you divide 9 by 8? It's 1. 1 is in the set. It's the identity. 1 is the identity, yeah. 1 times 1 is 1, 1 times 3 is 3, 1 times 5 is 5, 1 times 7 is 7. That should be mentioned. This also means 3 is its own inverse. 3 inverse equals 3 mod 8. Because when you multiply it by itself, you get the identity. 5 times 5 is 25. What's 25 mod 8? Divide 25 by 8, you get 3 with a remainder of 1 again. This is 1 mod 8. So 5 is also its own inverse mod 8. Interesting. How about 7? 7 times 7 is 49. Divide 49 by 8, you get a quotient of 6, a remainder of 1. That's 1 mod 8 as well. 7 is also its own inverse mod 8. Interesting. 1 is also its own inverse. Every element is its own inverse in this group. Weird, but true. The associative property does work. We can also multiply other things. 3 times 5, for example, is 15. What's 15 mod 8? Should practice doing these calculations quick. What's 15 mod 8? 7. Yeah, divide 15 by 8. You get a quotient of 1 and a remainder of 7. 15 is 7 mod 8. Should always add the extra mod. Sometimes at the end, sometimes you can do it in the middle. It's not a big deal. 3 times 7 is 21. What's 21 mod 8? Divided by 8, you get 2, remainder 5. It looks like closure's working. We haven't verified every possibility here. Being commutative, being abelian, I mentioned that word I think last week, is not necessary as far as groups go. Groups of matrices are typically not abelian, not commutative. This one is. This one's commutative. It's abelian. Some groups are, some groups are not. You'll see in the book discussion of the symmetries of a regular n-gon is called the dihedral group of order 2n. By the way, you might wonder what an n-gon is. Well, n is greater than or equal to 3. A regular 3-gon is an equilateral triangle. A regular 4-gon is a square. A regular 5-gon is a pentagon that has all the same side lengths and all the same angles, which I cannot draw very well. A regular 6-gon is a hexagon with all the same side lengths and all the same angles. A regular 7-gon is, I forget the name, heptagon maybe? I might be wrong. Regular 8-gon would be an octagon, yeah. Okay. Such objects have symmetry. D8, for example, represents the group of all symmetries of a regular octagon. Symmetries are really functions that preserve the shape, essentially. Either rotations by a certain angle or reflections across some line. You'll see that in the reading if you haven't already. I will talk about that much more on Wednesday. Let's quickly review equivalence relations and talk about them some more in the context of what we're doing here. So this is going to be quick. Given a non-empty set S, informally speaking, an equivalence relation on S is a correspondence satisfying. Okay, here we go. Reflexive property, symmetric, transitive, RST. I said it wrong in lecture 2 as far as Aristotle, Plato, and Socrates, and that was why I saw some confused looks. How's it go? It goes, see if we can get it right. Aristotle was Plato's student, and Plato was Socrates' student. I accidentally said Plato's student was Socrates' student. Aristotle was Plato's student, and Plato was Socrates' student. A, P, S in alphabetical order. Just remind me of that. RST, reflexive property, everything's equivalent to itself. Symmetric property, if A is equivalent to B, then B is equivalent to A. And transitive property, if A is equivalent to B and B is equivalent to C, that implies A is equivalent to C. Okay, very quick review. Should know this for the rest of the course. By the way, I did forget to mention, I think, our exams are closed book, closed notes. So you do want to memorize things. Okay, including definitions and theorem statements. That's the main reason that I do closed book, closed notes for these exams, is because part of the exam is restating definitions and theorem statements, at least the most important ones. And this is something you should be able to restate. Key fact is equivalence relations partition and vice versa. This is fundamental. Okay, it's a little strange, but it is fundamental. This is what I drew the picture on the board of last time. If you've got an equivalence relation defined in a set, it automatically causes a partition on that set, causes that set to be broken up into pieces. Subsets that are disjoint, intersection is empty, but whose union is all of the set. It's a fundamental thing. two elements, little a and little b, are in the same set if and only if they are equivalent to each other. That's how you decide what capital A will be. Take one element and look for all the elements that are equivalent to it. That is your set, say capital A. Then you create the next set in the partition, call it capital B maybe. Take another thing that's not equivalent to one of the original ones. Look for all the things that's equivalent to that new thing. That's the next set in the partition, call it capital B. And you keep going. And it goes the other way too. If you do have the set broken up into pieces, that induces an equivalence relation. Two elements will be equivalent if and only if they are in the same subset of the partition. So those two elements are equivalent to each other, but this element and that element are not equivalent to each other. Okay? Fundamental fact that we will make use of this. Right now I want to make use of this for another way to look at Zn. Okay? What I'm about to describe is kind of weird, but pretty important. Okay? Messed up my animation. Didn't want that there yet, but it's there. Remember, we use a bunch of different symbols for equivalence relations. Sometimes this, sometimes this, sometimes this, sometimes this, sometimes this. That's a traditional thing to use in the equivalence relation I'm about to describe. We can define an equivalence relation on Z, the integers, by the following condition. And it's got a name. It's called congruence modulo n. A is equivalent to B if and only if, for this fixed n is given to be a positive integer here. If and only if n divides A minus B. Remember this notation? Divides. A is equivalent to B if and only if n divides A minus B, which is equivalent if and only if to saying there exists another integer k so that A minus B is k times n. Okay, I could have used just one of those if and only ifs. I chose to put them both because they're both helpful ways of thinking about it. So we can take a particular n, like say 4, and ask, okay, for this n, well, let's not pick a particular one at first. Let's see why this is an equivalence relation. So again, we're given a fixed integer n greater than 0. Is A equivalent to A? Congruent to A, mod A. Yeah. Since A minus A is 0, and 0 is a multiple of n. I didn't put the mod n there, but I could have. It's traditional to go ahead and put the mod n here. Let's use the second form of what it means over there. A being equivalent, congruent to B mod n implies there exists an integer k such that A minus B is k times n. A minus B is an integer multiple of n. Is B minus A an integer multiple of n? Yeah, right? Because just multiply both sides by -1. And you write it like that. And since k is an integer, negative k is also an integer. And that means B is equivalent to A or congruent to A mod n. The word congruence here, mod n, is just a special phrase to use in this situation. But this is an equivalence relation. And the transitive property holds as well. I'm not going to write it as a question. But let me just write down some equations to help you believe it. These two facts, if I assume those are true, that will imply there exist two integers, call them k1 and k2. Such that a minus b is k1 times n, and b minus c is k2 times n. And you had a problem similar to this in the first homework. That's going to imply, if you add these equations, that a minus c will be k1 plus k2 times n. A minus c will be an integer multiple of n. And therefore, a will be congruent to c mod n. The transitive property will work as well. So it is an equivalence relation, and therefore it partitions the set of Z into equivalence classes for any given integer. What's that notation? Remember, you've seen this. That's the equivalence class containing A, the set of everything in Z that's equivalent to A. Meaning, really, the set of all numbers of this form. A plus k times n, where k is an arbitrary integer. N is fixed here. In the set here, k is the variable, so to speak. You subtract a from this, and you'll get a multiple of n. Those are all the things that are congruent to a mod n. So, for example, if a is 3, and n is 4, let's go ahead and do a particular example now. If n is given to be 4, and a is 3, the equivalence class of 3 mod under congruence mod 4 contains everything that is a multiple of 4 units away from 3. So that would include 3 plus 4 is 7, 3 plus 8 is 11, 3 plus 12 is 15, etc. Also, 3 minus 4 is -1, 3 minus 8 is -5, 3 minus 12 is -9, etc. That would be the equivalence class of 3 in mod 4, based on this equivalence relation that's called congruence mod 4. The equivalence class of 1, this is worth all writing out, I think, is going to be created in a similar way. There would be an equivalence class for 2 and an equivalence class for 0. That could be written in the same way. And you could also write equivalence classes of other numbers, but they would equal one of these. The equivalence class of 4 would be the same as the equivalence class of 0. The equivalence class of 7 is the same as the equivalence class of 3. 7 is in there too. And overall, then, this partition that is induced by this equivalence relation has 4 subsets in it. Even though Z is infinite, this partition has 4 subsets in it. I'm describing them more abstractly here. What I'm about to say the division algorithm guarantees that there exists unique Q and R, where R satisfies this property. It's one of those n numbers that makes this true. And so what I'm trying to say here is A could be an arbitrary integer, but typically we represent the equivalence class containing A by the thing that it's equivalent to in this set. Use this number as sort of the best representative. And you can define addition on the collection of equivalence classes to make this a group by this formula here. You can think of it in any of these ways here. given two equivalence classes, we can add them either by doing this or figuring out the simplest representative, R1 and R2, by the division algorithm and doing this. So for example, back over here, if I want to add the equivalence class of 3 and the equivalence class of 2, I could either say that's the equivalence class of 3 plus 2, which is the equivalence class of 5, which is the same as the equivalence class of 1. And I guess since 3 and 2 are already less than 4, that's the way I would think about it. I could also write an equation, for example, like this. The equivalence class of 8 plus the equivalence class of 9. I could either reduce 8 and 9 mod 4 first. 8 is the same as 0, 9 is the same as 1 before adding to get this one. Or I could add them internally first, like this, to get 17 and reduce that mod 4 to get the same answer. This is all in mod 4 arithmetic, and is full. This is really hard to get your mind around, I know, especially at 8 o'clock in the morning here. We have to have our quiz here in a minute. But this is actually really important. And I would strongly encourage you to think about it more after class. We will discuss it more. This is not the last time we're going to see this. Okay? But let's take the quiz.